In mathematics, a metric space is a set for which distances between all members of the set are defined. Those distances, taken together, are called a metric on the set. A metric on a space induces topological properties like open and closed sets, which lead to the study of more abstract topological spaces. The most familiar metric space is three-dimensional Euclidean space. In fact, a metric is the generalization of the Euclidean metric arising from the four long-known properties of the Euclidean distance. The Euclidean metric defines the distance between 2 points as the length of the straight-line segment connecting them. Other metric spaces occur, for example, in elliptic geometry and hyperbolic geometry, where distance on a sphere measured by angle is a metric, and the hyperboloid model of hyperbolic geometry is used by special relativity as a metric space of velocities. History. Maurice Fréchet introduced metric spaces in his work Sur quelques points du calcul fonctionnel, Arendic. Circ. Mat. Palermo 22-1-74. Definition. A metric space is an ordered pair whereas a set N is a metricon, i.e., a function such that for any, the following holds. The first condition follows from the other three. Since for any, the function is also called distance function or simply distance, often, is omitted and one just writes for a metric space if it is clear from the context what metric is used, ignoring mathematical details. For any system of roads and terrains, the distance between two locations can be defined as the length of the shortest route connecting those locations. To be a metric, there shouldn't be any one-way roads. The triangle inequality expresses the fact that detours aren't shortcuts. Many of the examples below can be seen as concrete versions of this general idea. Examples of metric spaces: the real numbers with the distance function given by the absolute difference, and more generally Euclidean space with the Euclidean distance, are complete metric spaces. The rational numbers with the same distance also form a metric space, but are not complete. The positive real numbers with distance function is a complete metric space. Any normed vector space is a metric space by defining. See also metrics on vector spaces. Examples. The Manhattan norm gives rise to the Manhattan distance, where the distance between any 2 points, or vectors, is the sum of the differences between corresponding coordinates. The British Rail metric on a normed vector space is given by for distinct points and, more generally, can be replaced with a function taking an arbitrary set of non-negative rails and taking the value at most once. Then the metric is defined on by for distinct points and. The name alludes to the tendency of railway journeys to proceed via London irrespective of their final destination. If is a metric space and is a subset of, then becomes a metric space by restricting the domain of to the discrete metric, where if and otherwise, is a simple but important example, and can be applied to all sets. This, in particular, shows that for any set, there is always a metric space associated to it. Using this metric, any point is an open ball, and therefore every subset is open and the space has the discrete topology. A finite metric space is a metric space having a finite number of points. Not every finite metric space can be isometrically embedded in a Euclidean space. The hyperbolic plane is a metric space. More generally, if is any connected Riemannian manifold, then we can turn into a metric space by defining the distance of 2 points as the infimum of the lengths of the paths connecting them. If is some set N is a metric space, then the set of all bounded functions can be turned into a metric space by defining for any 2 bounded functions, and this metric is called the uniform metric or supremum metric, and if is complete, then this function space is complete as well. If X is also a topological space, then the set of all bounded continuous functions from 2 will also be a complete metric if M is. If is an undirected connected graph, Then the set of vertices of can be turned into a metric space by defining to be the length of the shortest path connecting the vertices, and in geometric group theory this is applied to the Cayley graph of a group, yielding the word metric. The Levenshtein distance is a measure of the dissimilarity between two strings and defined as the minimal number of character deletions, insertions, or substitutions required to transform into. This can be thought of as a special case of the shortest path metric in a graph and is one example of an edit distance, given a metric space and an increasing concave function, such that if and only if, then is also a metric on. Given an injective function from any set to a metric space, defines a metric on. Using T-theory, the tight span of a metric space is also a metric space. The tight span is useful in several types of analysis. The set of all bimatrices over some field is a metric space with respect to the rank distance. The Helly metric is used in game theory, open and closed sets, topology and convergence. Every metric space is a topological space in a natural manner, and therefore all definitions and theorems about general topological spaces also apply to all metric spaces. About any point in a metric space we define the open ball of radius about as the set. These open balls form the base for a topology on M, making it a topological space. Explicitly, a subset of is called open if for every in there exists and such that is contained in. The complement of an open set is called closed. A neighborhood of the point is any subset of that contains an open ball about as a subset. A topological space which can arise in this way from a metric space is called a metrizable space. See the article on metrization theorems for further details. A sequence completion, which is a complete space that contains the given space as a dense subset. For example, the real numbers are the completion of the rationals. If is a complete subset of the metric space, then is closed in. Indeed, a space is complete if it is closed in any containing metric space. Every complete metric space is a bare space. Bounded and totally bounded spaces. A metric space M is called bounded if there exists some number I, such that D are for all x and y in M. The smallest possible such R is called the diameter of M. The space M is called precompact or totally bounded if for every R greater than 0 there exist finitely many open balls of radius R whose union covers M. Since the set of the centers of these balls is finite, it has finite diameter, from which it follows that every totally bounded space is bounded. The converse does not hold, since any infinite set can be given the discrete metric under which it is bounded and yet not totally bounded. Note that in the context of intervals in the space of real numbers and occasionally regions in a Euclidean space Rn, a bounded set is referred to as a finite interval, or finite region. However, boundedness should not in general be confused with finite, which refers to the number of elements, not to how far the set extends. Finiteness implies boundedness, but not conversely. Also note that an unbounded subset of Rn may have a finite volume. Compact spaces. A metric space M is compact if every sequence in M has a subsequence that converges to a point in M. This is known as sequential compactness and, in metric spaces, is equivalent to the topological notions of countable compactness and compactness defined via open covers. Examples of compact metric spaces include the closed interval 0, 1, with the absolute value metric, all metric spaces with finitely many points, and the Cantor set. Every closed subset of a compact space is itself compact. A metric space is compact if it is complete and totally bounded. This is known as the Heine-Borel theorem. Note that compactness depends only on the topology, while boundedness depends on the metric. Lebesgue's number lemma states that for every open cover of a compact metric space M, there exists a Lebesgue number, delta, such that every subset of M of diameter less than delta is contained in some member of the cover. Every compact metric space is second countable, and is a continuous image of the Cantor set. Locally compact and proper spaces. A metric space is said to be locally compact if every point has a compact neighborhood. Euclidean spaces are locally compact, but infinite-dimensional Banach spaces are not. A space is proper if every closed ball y, dr is compact. Proper spaces are locally compact, but the converse is not true in general. Connectedness. A metric space is connected if the only subsets that are both open and closed are the empty set in itself. A metric space is path connected if for any 2 points there exists a continuous map with them. Every path-connected space is connected, but the converse is not true in general. There are also local versions of these definitions: locally connected spaces and locally path-connected spaces. Simply connected spaces are those that, in a certain sense, do not have holes. Separable spaces. A metric space is separable space if it has a countable dense subset. Typical examples of the real numbers or any Euclidean space. For metric spaces, separability is equivalent to second countability and also to the Lindelof property. Types of maps between metric spaces. Suppose on are two metric spaces. Continuous maps. The map F, M1, M2 is continuous if it has one of the following equivalent properties. General topological continuity for every open set U in M2. The pre-image F-1 is open in M1. This is the general definition of continuity in topology. Sequential continuity. If is a sequence in M1 that converges to X in M1, then the sequence converges to F in M2. This is sequential continuity, due to Eduard Heine. Epsilon delta definition. For every X in M1 and every epsilon greater than 0 there exists delta greater than 0 such that for all Y in M1 we have. This uses the definition of limit, and is due to Augustin Louis Cauchy. Moreover, F is continuous if and only if it is continuous on every compact subset of M1. Uniformly continuous maps. The map F, M1, M2 is uniformly continuous if for every epsilon greater than 0 there exists delta greater than 0 such that every uniformly continuous map F, M1, M2 is continuous. The converse is true if M1 is compact. Uniformly continuous maps turn Cauchy sequences in M1 into Cauchy sequences in M2. For continuous maps this is generally wrong. For example, a continuous map from the open interval onto the real line turns some Cauchy sequences into unbounded sequences. Lipschitz continuous maps and contractions. Given a number k greater than 0, the map F, M1, M2 is k Lipschitz continuous if every Lipschitz continuous map is uniformly continuous, but the converse is not true in general. If chi less than 1, then F is called a contraction. Suppose M2 equals M1 and M1 is complete. If F is a contraction, then F admits a unique fixed point. If M1 is compact, the condition can be weakened a bit. F admits a unique fixed point if isometries. The map F, M1, M2 is an isometry if isometries are always injective. The image of a compact or complete set under an isometry is compact or complete, respectively. However, if the isometry is not surjective, then the image of a closed set need not be closed. Quasi-isometries. The map F, M1, M2 is a quasi-isometry if there exist constants A1 and B0 such that and a constant C0 such that every point in M2 has a distance it most c from some point in the image F. Note that a quasi-isometry is not required to be continuous. Quasi-isometries. Compare the large-scale structure of metric spaces. They find use in geometric group theory in relation to the word metric. Notions of metric space equivalence. given two metric spaces and they are called homeomorphic if there exists a homeomorphism between them. They are called uniformic if there exists a uniform isomorphism between them. They are called isometric if there exists a bijective isometry between them. In this case, the two metric spaces are essentially identical. They are called quasi-isometric if there exists a quasi-isometry between them. Topological properties. Metric spaces are paracompact Hausdorff spaces and hence normal. An important consequence is that every metric space admits partitions of unity and that every continuous real-valued function defined on a closed subset of a metric space can be extended to a continuous map on the whole space. It is also true that every real-valued Lipschitz continuous map defined on a subset of a metric space can be extended to a Lipschitz continuous map on the whole space. Metric spaces are first countable since one can use balls with rational radius as a neighborhood base. The metric topology on a metric space M is the coarsest topology on M, relative to which the metric D is a continuous map from the product of M with itself to the non-negative real numbers. Distance between points and sets, Hausdorff distance and Gromov metric. A simple way to construct a function separating a point from a closed set is to consider the distance between the point and the set. If is a metric space, S is a subset of M and X is a point of M, we define the distance from X to S as where represents the infimum. Then D equals 0 if and only if X belongs to the closure of S. Furthermore, we have the following generalization of the triangle inequality, which in particular shows that the map is continuous. Given two subsets S and T of M, we define their Hausdorff distance to be where represents the supremum. In general, the Hausdorff distance dH can be infinite. Two sets are close to each other in the Hausdorff distance if every element of either set is close to some element of the other set. The Hausdorff distance dH turns the set K of all non-empty compact subsets of M into a metric space. One can show that K is complete if M is complete. One can then define the Gromov-Hausdorff distance between any two metric spaces by considering the minimal Hausdorff distance of isometrically embedded versions of the two spaces. Using this distance, the class of all compact metric spaces becomes a metric space in its own right. Product metric spaces. If a metric space is, and n is the Euclidean norm on Rn, then is a metric space, where the product metric is defined by and the induced topology agrees with the product topology. By the equivalence of norms in finite dimensions, an equivalent metric is obtained if n is the taxicab norm, AP norm, the max norm, or any other norm which is non-decreasing as the coordinates of a positive n-tuple increase. Similarly, accountable products of metric spaces can be obtained using the following metric. An uncountable product of metric spaces need not be metrizable. For example, is not first countable and thus isn't metrizable. Continuity of distance. It is worth noting that in the case of a single space, the distance map is uniformly continuous with respect to any of the above product metrics, and in particular is continuous with respect to the product topology of quotient metric spaces. If M is a metric space with metric D, tilde is an equivalence relation on M, then we can endow the quotient set M tilde with the following metric. Given two equivalence classes, X and Y, we define where the infimum is taken over all finite sequences and with. In general, this will only define a pseudometric, i.e., does not necessarily imply that. However, for nice equivalence relations, it is a metric. The quotient metric D is characterized by the following universal property. If is a metric map between metric spaces satisfying F equals F whenever, then the induced function, given by, is a metric map. A topological space is sequential if and only if it is a quotient of a metric space.